Welcome to Spring LIB.
Okay, in this problem, we have incoming green light impinging on the human eye, and we're asked to determine what the frequency and energy of individual photons would be for that green light. We're also asked to consider, say, if one photon were to impact a tiny bacterium and transfer all of its energy to that bacterium, how much velocity would that bacterium gain? So this is kind of an interesting problem to solve. We know that the wavelength of this light is 505 nanometers, making it green light. And we know that the mass of this bacterium is some very, very small number, 9.5 times 10 to the negative 12 grams. Now, the equations that we need to actually solve all these questions are quite simple. We need to relate the wavelength of light, which we have, to the frequency in some manner, which we can do using c equals lambda f. In other words, the speed of light, which is unchanging, is equal to the product of wavelength and frequency, which can both change opposite each other. The energy of light is only related to its frequency, or equivalently its wavelength, and it's equal to hf, where h is the Planck constant. And I've quoted it here in joule seconds. The last piece of information we need to know is that the kinetic energy is equal to 1/2 mv squared, which I hope we all know at this stage. So let's jump into this problem. So let's start by finding the frequency. We can use the first equation quoted, that c equals lambda f. We know what lambda is. We need to find what f is. So this is equivalent to saying that the frequency is equal to c over lambda. We can immediately solve for this, or rather calculate it, where our lambda is 505 nanometers, so e to the negative 9 meters. This will give us a result of 5.94 e to the 14 hertz. So this is our frequency of incoming green light. Finding the energy for these photons is just as simple. We can simply take our frequency, which we just solved for, insert it into this very simple expression, and multiply. So this is our 6.626 e to the negative 34 joule seconds, multiplied by our frequency, which we just solved for, 5.94 e to the 14, 1 over seconds, because that's the definition of hertz. And this will come out to be about 3.94 e to the negative 19 joules. Great. And we can also, if we want to get this result in electron volts, which I think would be perhaps more appropriate, we can simply note that 1 electron volt is equal to 1.6 e to the negative 19 joules, so we could simply divide this number in joules. If we were to do that, we would end up with 2.46 electron volts. That's just when we're considering single photons, it's probably more appropriate to use electron volts as our unit so that we don't result in extremely tiny numbers, for example, to the negative 19th power. Okay, so this is the energy of a single photon. Let's say that all of that energy was transferred to kinetic energy of a bacterium. So we could say E equals K, the kinetic energy of that bacterium. And we know that K can be broken down in terms of mass and velocity. We're given the mass of the bacterium, so we just need to solve for velocity. Thus, the velocity of this bacterium is going to be simply the square root of 2 times the incoming energy over the mass. Excellent. And crunching these numbers, we have 2 to the 3.94 e to the negative 19 joules that we just found per photon. Divide by this very tiny mass for the bacterium, which, as you recall, is 9.5 e to the negative 12 grams, which would be negative 15 kilograms. Crunching these numbers gives us a result of 9.1 e to the negative 3 meters per second. So as you can see, even for something as tiny as a bacterium, one photon worth of light cannot transfer very much kinetic energy to this bacterium. Well, at least it can't get it to appreciable speeds. So here are the three results we were asked to find. We found the frequency of individual photons for green light. We found the energy of individual photons for this green light. And we found what the velocity gained would be if this light were converted directly into kinetic energy for a bacterium. Okay, thank you.